So say we have some function y equals u to the n, where u itself is a function of x. So we know by the chain rule, if we want to differentiate this with respect to x, then we'd get nu to the n minus 1 power times du dx. So, that means, whenever we have a formula for differentiation, we can just go backwards and get a new integration formula. So that means if we start with dy dx equals some function u to the n times du dx, then if we go backwards, if we integrate this with respect to x, then we should just get u to the n plus 1 power over n plus 1 and then plus c. So notice how the du dx just disappears when we integrate. So another way to think about it, more generally without the power rule. So say there's some function capital F, and the derivative, this is the antiderivative of little f of x. So the derivative of capital F of x is little f of x. So say we have f is a function of u. So we have u plugged into this capital F function. So capital F is a function of u, and u is a function of x. So if we differentiate this with respect to x, then we know by the chain rule, we'll get f prime of u times u prime, which we can also write as little f of u, since this is the derivative of this capital F, times du dx. So this tells us if we start with little f of u times du dx, and we integrate with respect to x, then we get back to this original here, just capital F of u, and the du dx disappears. So let's look at some examples of this. So here we have dy dx equals 5 times x squared plus 1 to the 4th power times 2x. So the important thing is choosing the right u to get it to integrate. So you want to choose a u so that you can see the du dx is already there. So we can choose u is equal to x squared plus 1, and then you can see du dx is 2x, and you can see 2x is already in the integrand. So, it'll cancel out easy. So if we make this substitution, we just have 5 times u to the 4th times du dx. And then if we want to integrate this with respect to x, the du dx just disappears, and we just take the antiderivative of this other part here. So this will be, raised to the power of 5 divided by 5 plus c. So u is just u to the 5th plus c. And then last step, you just plug in what u was in terms of x. So we have x squared plus 1 to the 5th power plus c. So another example where du dx is not exactly in the expression. So we have dy dx equals x over the square root of x squared plus 1. So now we're looking, let's say u is x squared plus 1. Well, that means du dx is 2x, but which isn't here. But notice that we have an x, so all we need is a 2. And so what we can do is we can basically multiply this expression by 2 over 2. Because, see, we can write 1/2 times this stuff times 2x. That's the same thing as this. We just added a 2 on the top and bottom. But now we have this du dx right in the expression. We just created this extra 1/2 in the process. So now we have 1/2 times u to the negative 1/2 times du dx. And so to integrate, this du dx is going to go away. We can bring out the constant. So integral of u to the negative 1/2 that's going to be raised to the power raised 1, so we have u to the 1/2 divided by 1/2, which is the same thing as multiplying by 2. So we have y equals u to the 1/2 plus c. And then again, we plug back in u in terms of x. So we're going to do one more example with a different way to think about how we're doing this changing to u. So let's say we have dy dx is equal to tangent of x. So this is an important function to know how to integrate. So the way you do it is you think of tangent as sine x over cosine x. And then we can use what we've been doing, because the derivative of cosine x is negative sine x, which you see is in the expression. So this is kind of the more common way to think about this process. So we say u is equal to cosine x. Okay, so then du dx is equal to negative sine x. And so now we can say that du is equal to negative sine x dx, or in other words, dx equals du over negative sine x. Because so first let's write the integral of what we're taking. So we want to find the integral of sine x over cosine x with respect to x dx here. So we set it at u, and we found an expression for dx in terms of the u. So we just substitute this into the integral. So we now have sine x over cosine x times du over negative sine x. And so now the sine x will just cancel out. We can bring the negative one out of the integral. And cosine x is a u, so we have 1 over u du. And well, the integral of 1 over u is the ln of the absolute value of u. So evaluating the integral, we have ln absolute value u plus c, which, plugging back u in terms of x, negative ln of cosine x plus c. So again, this is the more common way to think about the process. You decide what u is, and then when you find du dx, you can solve for dx in terms of du and some function of x, and then you plug that into the integral and cancel things out. Or you can think of it, how can I get du dx directly in the expression?